Okay. Sorry.
Like deletes the video, or if that is the event. I don't really want to deleting the video.
That's good. That's good enough for me. You ready to? Okay. Good. Yes. Everybody gathered around my iPad. Okay, let's get started. There's a lot to get through today. Hopefully. I'm excited. I'm super excited. Does anybody know why I'm super excited? I do actually love MVPs. MVPs are super exciting. After today, you will have the tools you need to solve something, which is really exciting. Last time I just kind of described what they were. Today we're going to solve them. If we're fast, we may even touch on reinforcement learning at the end of the lecture today, which I'm super stoked for. So yeah, let's do it. Also, I've had too much coffee, so that might. Okay, MVPs 2. Before we get started, questions from last time? Yes?
So the scores unmuted, is that a new quiz policy?
That is a new accidental quiz policy. You will be able to see your scores after I fix that today. Do note that, again, there was a due date that was different than the available until date. The due date is still the due date, so if you did it late, I commend you. If you didn't have a good excuse for doing it late, though, there's no late points on quizzes, just on assignments. So, anyway, I'll fix that. Sorry about that.
So just to be clear, that's not the policy going forward, that was just a one-time.
That was a one-time deal. The exception being that I don't know offhand how to make. I want to keep it open in case like somebody's in a car accident or something has a good excuse for not being able to do it. So were you to do it late and I haven't filtered it yet, you would see a score that wouldn't actually be correct. Or if they were up scores, you don't see it now. Anyway, no, it won't be the policy. You'll be able to see it. Okay. Other questions? Yes?
When are we going to start the Project 1 grades?
Project 1 grades
Next week?
next week, early next week, I think, probably. Yeah. Cool. Similarly with homework 1 grades, hopefully later this week. We hope. Yeah. All right. Other questions? Yes.
Project 2, when should we expect this?
That will come as soon as we can vet Python 3 version of Project 2 sufficiently. So yes. So this semester we have made the transition from Python 2 to Python 3 for the first time in the history of CS 4300. And in fact, 6300, the grad version of this class, I think, before spent use Python 2. So, yeah, John's with Python 2. What are you doing? No. Anyway, so we have to work out some bugs with this, right? So things are kind of a little guinea pig tests to make that transition, but we appreciate your patience and bearing with us in that process. It will benefit both you who need to use Python 3, which probably makes more sense moving forward, and also the next few semesters as well. So, yes? There was not a quiz last week, and that was because I wanted to give you Project 1 in a not distracted state. That will not be the case going forward. So moving forward, there will be times where there are quizzes, homeworks, projects contemporaneously at the same time. So you have to manage your time. But again, the quizzes should be very short. The homeworks should be relatively short, and the projects will be the more time. Cool. Yeah. Other questions? Okay. MVPs, part 2. We're going to wrap up part 1 first. Okay, so let us revisit a couple things we did last time so that we can build on this time. But we introduced this running example of MVPs last time. So we have this grid world, right? And here we have this maze and this agent that lives on this grid. They can move up, down, left, or right, north, south, east, or west, equivalently. There are squares it can't move into. That's the maze part. There are squares that after it ends its turn in that square, it gets some reward, a positive one in the case of the gem, a negative one in the case of the pit of fire. And then we also have this kind of living reward, right, where there's some negative cost associated with taking a step. Big rewards come at the end, good or bad. Does everybody remember this? And then the goal is to maximize the sum of expected rewards. Right? So this is an example of an MVP. It is just one. Most MVPs, almost all MVPs, functionally all MVPs in the limit don't look like it. Right? This is just an example. Okay. So MVPs in general, we have this set of states S, right? From that, we can choose an action, and we have these transitions, right, that map state and action pairs to resulting states with some probability, right? So T of SA S prime here is equivalently the conditional probability of arriving at S prime given you started at S and chose action A, right? We also have rewards. In general, those rewards are going to be a function of all three of those values, right? So what that looks like is that reward exists on this edge, or equivalently, it exists when you arrive here. Yes?
So the function T that returns the probability.
Yes. Exactly. Okay. And then in order to actually act on this, we would need some notion of a start state, right? So all of this is given to us in advance, right? And then we want to reason over this and determine something called a policy, which is going to map our set of states to an action, right? So for every state, the policy describes an action. And that policy could be good. It could be an action that does something good for us. It could be bad. It is just something that maps every state to an action, right? Okay. So our goal kind of in solving MVPs is to come up with a good policy, right? And so this is different from search because we may decide to take an action and then something unexpected happens, we don't land where we wanted to, right? So it's not enough to just say, this is the path you should take, right? Because at some point, via chance, you're going to deviate from that plan, potentially, right? And now you need to know what to do. I'm no longer on the path that I determined, right? And so I need some policy that maps all of the possible states to a good action, right? And so the process of solving MVPs is reasoning over this progressing concept of these probabilities and transitions and values so that we can take good steps anticipating what may happen in the future. Right? Does that make sense? Okay. So we have these quantities, right? This is a policy. This is what I've just been talking about. It maps states to actions. We have a utility, right? This is defined over a state. It is the sum of discounted rewards that we can expect to get from that state, given some policy. So if we have an optimal policy, then the utility would be the expected sum given that we have the optimal. Right? Yes?
Still considered a policy if you add in like an enemy with its own AI that's changing the dynamics?
So the notion of an enemy that's changing dynamics is kind of more specific than MVPs are in general. So I would say maybe. It depends. If you can map your specific problem where you have this notion of an enemy that's changing the world in some specific way, you're trying to interact with this world, trying to anticipate what the enemy's doing, if you can map that into this formalization, then you can solve it as an MVP. If you can't, then you'll get into different tools to solve it. So it really depends on what you're trying to do. So MVPs, this is an abstraction. You can map your problem to this abstraction. You can use tools that we have developed, we being the field of computer science and math, the tools that the field has developed to solve these in order to solve your problem. And that's like the art in AI, right? All of these problems are super hard, like capital H, NP, capital H, hard, right? Or worse, right? So really the art is in formalizing your problem into some abstraction that people have spent a lot of time coming up with good heuristic solutions for, right? That's kind of a philosophical concept here. But anyway, that's the general idea. Okay, so back to MVPs. We have this utility, right? It's the sum of discounted rewards. We have values. That's the expected future utility from a state, right? And we have Q values. That's the expected utility from a Q state. Does everybody remember what a Q state is? This is kind of a weird concept, so let's think about it again. These are our states, right? They are max nodes in our expect max search tree formalization. From here, we can choose an action. So we can choose which arrow we're taking out of this, right? Then we arrive at this expected max node, this expected value node, right? This is, we started at S, we chose A, but we don't yet know what's going to happen, right? So the implications of our action haven't hit yet, right? This, in our expected max formalization, is a different node, right, that you transition to via choosing A. And we call these Q nodes. Well, that's not a Q, that's a theta. Q nodes, and they have Q values. Right? Everyone remember this? Yes?
Is like the title Q state similar to like the Q bit title where it has like a probabilistic placement, basically?
Maybe? I don't know. That's a good question. I'll look into it. You can look into it.
I can see the parallel.
Yeah, sure. I mean, I'm not going to say it's not related. It might be coincidental. I'm not sure. Anyway, we'll see Q, the letter arrive being later when we talk about Q learning reinforcement learning too. So, yes?
So is the Q value the transition?
Q value is not the transition. The transition is some conditional probability.
Oh, okay. I thought that. Sorry.
So the Q value is, if we are here, right, in that we started in S, we chose A, and we don't know what's going to happen, it is the expected future utility, given that we act according to some policy or optimally in the more specific case. Right? Okay. So now we can have these optimal quantities defined over this, right? So V star of S, that's going to be the optimal, the expected value starting in S and acting optimally, right? So that's defined over the states, right? And it's the expected utility. Okay. Similarly, we can have a utility value, an optimal utility value of a Q state, right? That's the expected utility starting out in the Q state, which is equivalent to saying we started out having taken action A from state S, and after that, we'll act optimally. Those don't have to be the same thing, right? This could be, A could have been suboptimal, right? Defining a different Q state, which would have a different Q value, but you assume after this you act optimally, right? So under here, for every A, there is a Q state, right? This might be the optimal Q state, but these Q values are defined over these too, right? Does that make sense? And then so determining the action is really boiling down to looking at these values at the Q states, right? Okay. We also have this notion of an optimal policy. So remember we defined a policy via the character pi, right? It is a function over its states. It maps them to actions. The optimal one maps state S to the optimal action. Cool. All right. That's NDPs, the recap. This one layer, one kind of branch of an expected max search is a really, really good way to think about NDPs. So that's why we keep returning to it. Okay, so if we're looking at Gridworld, let's say that we want the values V star for every state. In this case, a state is a square, right? You remember this, we had the reward of +1 here, -1 here. There may be some negative reward for existing. There is some discount factor gamma, right, that is reducing the awards if they're further in the future. But given the MDP, then via some algorithm that we haven't talked about yet, but I'll describe here in a minute, we can solve for something arbitrarily close to the optimal values here. Yes?
The living value, is that actually subtracted from the actual value?
So there is no real actual value or a living value. If we look at just the MDP formalization, there are transitions that occur from state to state, right? Given some choice of action and some resolution of the chance, that transition has some reward associated with it. So we define all of the transitions that aren't leave this and leave this with that negative living reward, right? Leaving these states has their associated reward and not that reward, and then you just accumulate.
When you say living or negative living reward, are you just talking about subtraction?
It's a negative value that gets summed, so in that sense it is subtracted.
Okay.
But really, the right way to think about this is just there is some reward value associated with these transitions from state action pairs to states, and those get accumulated over time. Yes?
these state values constant under the assumption that we can revisit them, or are they singular?
Yeah, so that's a very good point. These are, okay, so these actual values are an approximation because this thing has infinite depth. Functionally speaking, we could just kind of stay in one state, bounce back and forth forever and ever and ever and ever and ever, right? The true V star values accounts for all of those possibilities, right? Like even under the optimal policy where we go up here, there's some chance that we actually stay here, right? Because 10% chance we go left and we actually stay in this square. There is some chance that that happens again and again and again and again and again and again, and we never go anywhere, right? So you have to account for all of these. And so the whole purpose of MDPs is to reason over all of the possible futures given the uncertainty that we've described and choose the optimal action given all of that uncertainty. Does that make sense? Yes.
So last time you talked about retaining structure, is that how you're figuring out those values, or are you going 100 layers deep?
I will tell you how we figure out these values here in a minute. Okay, so this is just a review of what the V stars look like, right? They're a value described over the states. They correspond to the expected sum of the cumulative rewards if we add optimal in that state. Right? And so this isn't exactly one because there with some probability we will go down and end up here, which is a bummer. Some probability we'll go up and stay here, which is less of a bummer but still a bummer, right? And then on and on and on down the implications of that. Yes?
If there's no probability that you go from side to side and you're in that square, would this value be 1 or would it be less just because there's a cost of being there and not on?
It depends on when you apply the discount. It would be less because you would have the negative 0.01 or whatever for transitioning and the discount. But yes.
How did we resolve at the same value for the middle, given that we had a chance of going right into the depth square on the right? So you think if you're factoring that into like your probability, that would be a subtraction on that future on the 0.57.
That's a good.
One row down, and there's the right, sorry, versus the one just down. I feel like it's safer and maybe it's further from the one, I guess. You lose, but.
So that's why. I mean, it's further, right? So while there is the chance that you end up here in this bad square, it's going to take you a while more longer to get here, and you're accumulating negative reward along the way. Then you also have to account for the chance that once you're here, you actually end up down here and go here anyway. This is really complicated to reason over, right? Like these things go on for forever. So that's what makes this not trivial. Right?
So is this like just a coincidence that they happen to come out to the same number?
Yes, as far as I'm concerned. I mean, I don't see the structure that would cause that to be easily explainable. It's just the way the numbers look at. Okay. So we also have these Q stars, right? This is conceptually a little more difficult to think about, but not really that complicated. You're in some state, right? So Q is defined over state action pairs, right? So if you're in this state here, and there is a Q star value for I'm here and I decide to go north, I'm here and I decide to go east, etc. Right? That's just what the Q states are. Okay, and this is 0.85 because I may be here and decide to go right into the good square, but actually end up down. Right? Okay, I'll review. Okay, so expanding on this notion of values of states, we can compute the expect max value as state the same way we've been computing expected max values all along. Right? It's the expected utility under optimal action. We take the average sum of discounted rewards that happen in the future. This is exactly what we were doing in expected max this entire time. Right? The problem is this thing might be infinitely deep. There's a bunch of them, right? And so to actually solve this, we need some better way to relate these values. And so what we use is a recursive definition of value, right? And so if we want V star of x, the one is this. We're acting optimally, right? So we have to consider all the actions, right? And what are we looking at for the actions? The values of what happens at the t, right? Easy. But we don't really have these, right? So what are those? Well, It's not the minimum.
The probabilistic value.
It is a probabilistic value, right? So what is the value, the expected value of being here and acting optimally thereon, right? So we have to account for all of these outgoing edges, right? So we're going to need to take the expected value, which is going to be a weighted sum of the values associated with those transitions, right? And so what happens with those transitions for each of these? Well, we get our reward now, right? Plus the expected future reward, assuming we act optimally from there on, right? And so we have at least a symbol that describes that, right? This is S prime here. And we discount it in the future, right? Cool, we're done, right? I've got something on the right-hand side of the equal sign for every value I care about. Maybe not, right? So this kind of seems a little bit like circular reasoning, right? I've defined B stars with respect to Q stars, and I've defined Q stars with respect to B stars. What a bummer. What do we do? Yes?
So, we know that we're going to be starting on some B star, probably, if we're making a decision Z, right? So from here, would we want to just define some sort of depth limitation to say, like, we only want to go so deep into the search, and that's where we basically end it?
I agree exactly with half of what you said. So, yes, we're going to depth limit something. That's going to be the insight from which we start to solve these things. But we're trying to compute a policy, so it's not really taking into account where we're starting,
Okay.
right? We have to do this for every state, right? Because at the end of the day, what we're concerned with is a policy. But yes, we're going to start depth limiting things in a second. Yes.
So, is beam search like a more general form of that?
So beam search is in like the machine learning version.
I don't know what version, but like.
Okay, so I may hit beam search later, much later in the semester.
Okay.
We'll see, but I'd like to live for that for now. Yes?
So we're gonna run this depth limited recursive algorithm on every state to kind of evaluate?
Yes. So we're going to have to do something for every state. This is only going to work when we have a manageable number of states for now. Right. So let's move on just for a minute and we'll talk about how we actually solve this in a depth limit way in a second. So I've defined this kind of mutual recursion, right? It seems like circular reasoning, but it's not circular reasoning, right? Because this is S prime here, right? So what I've really done is I've related B star to Q star to a different B star, right? One that's one layer down in my search tree. It's not circular, now it's a tree, right? Starting to look kind of familiar. So usually this is written in line, which looks like this here. These are called Bellman equations, named after somebody named Bellman, I believe. Or maybe he was a Bellman at the top. I don't know. No, I'm assuming it's called Bellman. Anyway, there are many Bellman equations. It's kind of a concept. These are an instantiation of Bellman equations, a type of equation called Bellman equation. But basically what it's doing is it's relating optimal values to different optimal values, right? Okay. It's just a system of equations at the end of the day. And so we can solve systems of equations. The problem is here, that max makes this nonlinear. And that's fun. So we have a bunch of tools that really effectively solve linear systems of equations. This is nonlinear, so it's not going to be that easy. Okay. So again, these are called the Bellman equations. You should get very comfortable with these. So stare at them for a long time. Print them out and like take them to bed with you. I don't know, whatever you want to do. Get comfortable with these equations though, because once you have your mind wrapped around what this is actually saying, then you're going to be a lot further down the road to intuitive understanding of MVPs and other things in the future that are going to relate to this. Yes?
I know this is probably a dumb question, but that the T function, that's the decay, right?
No, the T is not the decay. The gamma here is the decay. The T is the probability, the conditional probability that you arrive in S prime given that you started in S and chose A. So this sum over these conditional probabilities, that's an expected value. so this gamma here, that's the disk. Good question. Yes, so spend some time with these. We're going to see a variation of these, like 10 different variations of these later in lecture today. But yeah, Bellman equations, very important concept for all kinds of dynamic programming things, which is this kind of instance of. So spend some time with these. Okay, it'll be fun. I promise. All right. So we've defined the optimal utility of some state as an expect-to-max recurrence relationship, given that we've looked ahead one step, right? So we look ahead one step of expect-to-max, and then we have these optimal values, right? We've related the optimal value up here to the optimal value down there, right? That's how these equations work. Okay. So this is a set of equations. It's not really talking about how you solve them, right? So we'll talk about that later. What they're doing is they're characterizing the optimal values. They're saying the optimal values satisfy these properties with respect to each other, right? Okay. So let's revisit this racing example real quick. We have a car that wants to go really fast. You have three states. You can have a cool engine, you can have a warm engine, you can have an overheated engine. If you are overheated, you're done. Game over, right? You should reflect on your life choices. If you're in cool, you have two choices. You can go fast, you can go slow. In fact, if you're in cool or warm, you can have two choices. You can go fast, you can go slow, right? If you go fast, you get twice the reward, 2 in this case. If you go slow, you get 1. But if you go fast, there's a chance that you increase your warmth level by 1, right? And if you started out in cool, that chance is 50-50. If you started out in warm, that chance is certain 100% of the time you end up increasing, right? Does everybody remember this? Okay, so if we want to kind of conceptualize how we would run expect-to-max on this and determine kind of optimal actions, then we can formalize this kind of as the search tree, the similar way that we've been formalizing things in the past, right? So we can run expect-to-max on this, but maybe there's a better algorithm. And that's because we see, at the end of the day, there's just 3 states here, right? There's cool, there's warm, and there's overheated. So if we can start to relate these things by the Bellman equations, maybe we can do something better than just expect-to-max search. But if you just looked at the search tree and ran expect-to-max like we've been doing, it gets pretty wide pretty quickly, right? So it grows exponentially. But again, we've only got 3 states, so there's something exceptionally missing. Yes?
So what's to stop us from using like a solid state system or like a greedy algorithm for something as simple as this?
Well, so a greedy algorithm is not going to be optimal, necessarily. It's probably the definition of greedy. You said solid state,
Yeah.
like some finite state.
Exactly, like determine current state, make action based off current state, and then continue.
That is what we're doing.
Oh, perfect.
Yes. So if you don't think about this as a search tree, but instead think about this as a set of states with transition functions, right? This is a finite state machine. Right? So very, very intuitive question. Or good question. Good intuition. Okay. So the way this is kind of going to work is what we're going to do is we're going to start at the bottom of this tree, and we're going to work our way up. Okay? So if we did expect-to-max, we would do too much work. The issue here is that all these states repeat, right? There's 3 states over and over and over and over and over and over and over again. Their values depend on their depth, right? But not where they are necessarily. So we can just reuse this information in a way that I'll show you here in a second. Okay. But is there a bottom to this tree? There's not, right? Not the way we set it up. You just go slow forever, right? So what does the bottom even mean? Well, we do have this concept of discount, and as I mentioned last time, there's this conceptual idea that because this discount is compounding exponentially, things that are way, way deep matter almost not at all, right? And it's more the things that are close that matter, so we'll kind of build on that concept a little bit. But the idea here is that we're going to kind of depth limit this. And we're going to increase the depth until we have some convergence on state. Okay? But we can conceptualize that same process in a slightly different way, and it's good to think about both. So the idea here is that we say, I'm going to make this tree finite. There's a finite number of time steps I'm going to allow you to take in this game, right? You can drive fast or slow 100 times. That's it, right? Game over. So now, there is a depth to the tree, right? It stops, so we can conceptualize starting at the bottom and building up. That makes sense now. And the idea here is that we have some limit, some iteration k, and k is going to be v sub k. This is no longer v star, right? This is now a different thing. vk is the optimal value at s if the game ends in k more time steps, right? So v sub 0, or yeah, v sub 0 of s would be what happens if the game is over now. V sub 1 of s would be what's the value of the state if you get to take one action and then the game's over, etc. Right? Does that make sense? Okay. Equivalently, this is what a depth k expected max would give us from this. Okay. So let's look at that on this Gridworld example. So if the game ends in 0 more iterations, what are our values here? I mean, I've got them up there, right? So they're nothing, right? Because it takes an action to get a reward. You have no more actions to take. Everything's 0, right? What if we say there's one more action you can take? Okay, so in this case, there is no cost for living, no living reward, right? Just the rewards at these corners. So it's worth noting, this value is not just defined over the ones that have numbers. It's defined over every state, right? There is, so if you're in this state, you have one more action to take. What's your expected reward? What's the optimal reward that you can get starting there? It's 0, right? I mean, you can make a move, you're just not going to get any reward, right? So this v sub 1 is still defined over all the states. It's just that only 2 of them actually have actions available to them that would result in some reward. Yes?
So is there an exit action in this case? Do you have to
Yes, so that's how this is formalized. Basically, from the states that aren't these 2, you have your 4 actions. From these 2, you have 1 action available to you, it is exit. And with that state action pair, you get these values. So you have 1 action left to you. The only way to get reward in the case would be to have been in those states and choose the exit action, right? Okay. What if you have 2? Is there anything weird about this? Something different than you would expect, maybe? So this kind of makes sense, right? You want to go right, and then you could exit and get your 1, right? But with a 10% probability, you actually end up going up and staying here. With a 10% probability, you go down here and land here, but then you're out of action. Right? Well, you could move from there, you're just not going to be able to exit, right? So you won't get a reward from that. Yes?
So the little white arrows is like which one of the actions you should be doing those.
Yeah, so the arrows are just what the code said was the optimal action under this policy.
I'm confused about 2 of them. So the one in the previous state, when k equals 1, the arrow right just to the left of the hole, of the firing hole, pointed to the left, right? Like don't take any risk going into the hole, right?
Let's ignore the arrows for now. Some of those aren't going to have values yet, and it's just whatever they were initialized to potentially. But we'll ignore them for now. Yes?
Shouldn't the square next to the fiery hole have a negative value because there's a possibility it will go into the fiery hole?
That is exactly what I was hoping somebody would say.
Oh, that's interesting.
Why is that 0?
Oh, because you don't have enough actions to exit?
You do. You could go right and exit. We have 2 actions available to us.
We just haven't evaluated it yet. We just evaluated.
We have. Every state in this has been evaluated and the value is shown. Yes.
Because going up has a positive association, so the chance of it going to the right and the cost of accidentally going to the right versus the benefit of going up equal each other.
So if you go up, you don't get any reward. You go up, you go right, but then you don't have time to exit. So why is this 0?
I think in the description it said you only slip like left or right relative to the direction you want to move, so you can just move left from there.
But
And
the
then,
optimal arrow system.
The arrow says to go up, which means there's a possibility of.
Okay, let's ignore the arrows.
Let's ignore the arrows.
Ignore the arrows for now. Yeah, I think the arrows are not right here. Okay, this is 0 because this is the value of optimal play from that state, right? And there is a way to play from here that gets you 0. There is a way to play here that gets you -1 with some probability. But we have a way to guarantee it's 0. And so that is the optimal, that's the star, right? On the star here. Does that make sense? That's a little counterintuitive. Yeah, so ignore the arrow, but basically, if you go this way, I think it gets, anyway, yes.
For clarity purposes, are these arrows not part of the algorithm when they determine optimality, or were they part of the algorithm when determining optimality?
So the arrows are a policy, we're just talking about determining the values right now. So these things are related but not the same.
Okay.
But I will make them more concretely related later in the lecture. Okay, so what if it's 3? Well, now we have a choice from that square that would get us positive value, right? So the optimal play from there with some probability gets us that value. That's the expected value given the probabilities, right? Etc. Okay, so we keep increasing this. You see what's happening, right? And that's what it looks like after 100 iterations. So this is the value that says, given I will play optimally for 100 iterations, this is the expected sum of accumulated reward. Let's go back a second. All right, so at some point, the arrows started making sense. Let's assume they started making sense here. Watch the arrows. So the values were changing, the arrows were changing less frequently. Here we are at 12 iterations, here we are at 100 iterations. The policy's the same, right? So this is a property of the algorithm that this has been generated with, which is that generally the policy is going to converge much more quickly than the values do. And that's something that we're going to want to leverage later in the future. And that makes sense because we've got this max operator, right, at all of these layers. Max is throwing away a bunch of information. Very infrequently does something break the bound of what max is, right? It has to grow and grow and grow, and then it shrinks when it grows. It has to become greater than the thing that was greatest, right? That happens less frequently. Okay, anyway, the policy converges in general more quickly than the values do. It's the policy at the end of the day generally that we care about, so we need to leverage that later. Okay, but here's the idea. If this is 0, right? If you're in these states, you have 0 actions to take. We know what B star is for all of them, right? It's 0. Similarly, we know what the values, we can compute from those the values of B1 for each of these states, right? And they're going to be the same spanning the whole layer of the tree. So we only need to compute the 3. And on and on and on, right? We can start from the bottom. Okay, this process is an algorithm called value iteration. The idea is that we start with B sum 0. The rewards are 0 by our definition, right? No time steps left means no expected reward, means they sum to 0. So, given a vector of B sub k, what we can do is multiply the expected max from each state, right? And so that's this algorithm here. So this is an algorithm that looks like the Bellman equations. It would be the Bellman equations if these had stars instead of k's, and this wasn't a left arrow but an equal sign, right? But this describes an update rule, right? we start with sum b, we update it, we get b sub whatever that was plus 1. And go on and on and on, right? We can repeat this process until we converge to some values. And that will get us the values that each of us is. Right? So what's the complexity of each iteration of this? Let's see. So we have to look at all the a's, right? Right, and then we're summing over the s primes that are possible from our s, right? That's not actually a prime, but rather the cardinality of a, right, times cardinality of s potentially, because in the worst case there are s primes that we could achieve from any state, and then we have to do the whole thing from any state. Right? So what we're looking at here is right. So these are actual cardinals. But you see what I'm saying? So that's only going to work for manageable s's and manageable a's. Right? So if we have a humongous state space, this isn't going to work. If we have a humongous action space or continuous action space, whatever, this isn't going to work. Right? Yes?
Is this S squared under the assumption that every state can transition into every other state?
Yeah, so it's the worst case. That's not always going to be the case, and in fact, maybe most of the time it's not.
Yeah.
Right? Definitely in our grid world, it wasn't the case. You couldn't get to every other state from every state, just the adjacent ones. Right? So that might be smaller in practice. But for big S or big A, this is still an issue. Right? Okay. So we have this update step, right, that we repeat until it converges. I'm going to sort of prove to you in kind of a sketchy, hand-wavy way that it will converge later in the lecture if we have time. But the idea is that the approximations that are associated with each v sub k are going to get progressively and progressively closer to the true values in a converging way. And the key takeaway that I mentioned already was that the policy may converge long before the value. And if the policy is that you care about, it's worth noting.
Does that require gamma less than 1?
It does. The proof does require gamma less than 1. In fact, it requires both bounds on the minimum reward and the maximum reward and gamma in between 0 and 1, strictly less than 1. Otherwise, it's not going to converge. It could be infinite, right? Or negatively infinite, whatever. Yeah, good point. Okay, so the Bellman equations characterize the optimal values. That value iteration computes them. This is called a Bellman update. Okay. So if you've seen this kind of concept before, generally in other contexts, this is a fixed point solution method where we iterate until we try to find a fixed point for the equation, right? And then under some assumptions that solves our equation. Newton's method is another one. So, okay. This is solving for something that's arbitrarily close to the real optimal values under infinite time horizons, but you can also conceptualize it as k time limited, the actual solution to that. Does that make sense? Yes?
So if we do this until convergence, how are we measuring convergence in those cases?
It's a great question. So you could look at some thresholding on how the values are changing over time. You could look at a higher order of that and start to look at the slope of the change of the values. You could just say, I'm going to do it 1,000 times and call it a day. Up to you.
And that is all considered convergence.
Well, convergence just means what you want it to mean. It converges sufficiently such that it solves your problem. There are many definitions of convergence. Usually you choose what it means.
I guess it's converging anyway, so you just say like, oh, it has converged at whatever point.
So what I would do as a first pass is I would say I have some epsilon that's very small. I want my changes of the values to be smaller than that in the case of convergence. So if they're changing with some norm defined over the vector of values, whatever norm you want to use, that value is smaller than my predetermined epsilon, it's converged. If not, it's not. And that's like the easiest way to do it. It's not just say for i's 1 to 100, right? So that's probably that. But yeah, convergence means whatever convergence means. You get to kind of do that. It's really important to note that these updates are not happening in place. So you're not modifying these values as you figure them out. If you do that, I don't even know what happened. It'll be great, so don't do it. Okay. So let's look and run through an actual example of this concept, right? Okay. What's v sub 0? For all three states, right? There's nothing you can do. In fact, it's going to be 0 to these as well, right? Because if you find yourself in that state, the reward you can accumulate from then on is nothing, right? Why is that not -10 or whatever it is I put on?
It's because we calculated a reward after the last move, and we assumed we acted optimally.
Yeah, so we say, I mean, this is defined by saying I already am here. What's my expected value if I'm playing optimally from here? Right, it's 0 because I'm already there. There's no way to accumulate more rewards. It's over, right? And that value probably won't show up later because if we're playing optimally, we can avoid it. Right? Okay, so let's see. What is our value here?
1.
I'm cold. I have one more choice, and then the game's over. What should I do?
Go fast.
Floor it, right? There's only one more turn. Nothing bad can happen after that. So if I play optimally from here, given that there's one more time step, that's 2, right? What if I'm here? Floor it, and then get a -10.
Wait, why would we ever?
We wouldn't, no.
Okay.
Incorrect, sorry. But it was fun. But no, I do apologize. Anyway, we're playing optimally, so what do we do from here? Slow and accumulate the reward of 1. Okay. What about here? So let's assume there's no discount,
Yeah.
right?
So you go fast again now.
Well, let's look, right? Let's look at the equation. So we want to max over A's, right? So let's evaluate what happens if we go slow and what happens if we go fast, right? From here. So if we go slow, the possible states we can arrive in are what?
You'll either be cool or warm.
So we can just arrive in cool.
Yeah.
So we're in cool right now. We choose slow. What happens? We're going to stay cool, right? So there's only one S prime here. The probability here is 1, right? What reward do we get? 1 plus gamma is 1 here, right? Times V sub 1 of cool. Right? Well, we know V sub 1 of cool, right? We computed it last time. This is the key insight here. We have this value. We can plug it right in, right? So if we go slow, we get 1 times 1 plus 1, right? Somebody check my arithmetic here. Right, which gives us a value of 2. I don't know why I changed colors. Anyway, right? What happens if we go fast? Well, we use sum over possible states, right? There are going to be multiple of them in this case. So let's say we end up. All right, so we're going fast, right? We started in slow. T of staying slow is 0.5, right? And if that happens, then we get a reward of 1. plus 1, right? Does that make sense? And if we had instead arrived, no, this would be 2 plus 1, right? And if instead we had arrived in warm, I might be doing this wrong. This one's 2 plus 2? No. Okay, hold on.
Which one's cold and
Should
which
the top
one's
one
warm?
be 3? Yeah, I
Yes.
think the top one's 3.
Which top one?
This.
S to the cold should be 3 because V sub 1 is 2, gamma is 1, and we add on the current value of 1.
Oh yeah, so I put the wrong value in here. Alright, so this one's 3. Okay, so if we go fast, then with 0.5% probability, we end up slow, or we end up cool, right? So we get 0.5 times 2 for going fast, plus 2 because of this, right? And then with probability 0.5, we get 2 for going fast. This one's a 1, right? Okay. Is that right? Okay. And so you could do a similar exercise on my arithmetic stat, so I don't feel like it. For that. Okay, you get 2.5. Does this make sense? So we started then to define an algorithm that relates the values here, right, via some math to the values here, and on and on. Yes?
So in like the grid world, we're gonna be accumulating rewards all the time. In grid world, you can only ever get that one, right? And then how well we can get to that one.
So the rewards are defined over state, action, state, tuples, right?
Right. It's your transition step.
Yeah.
So
And that's an input to the problem.
yeah, so for in terms of convergence here, it seems like we're gonna like our values for the states are gonna go up and up and up, right? Whereas in the grid world, they kind of start to plateau. Really.
Yes, that's a great point. So will this converge?
Yeah. I don't think it'll convergence value. It'll convergence exchange. Maybe.
So without a discount, this is an infinite. This will just both will grow to infinity, or all policies that don't end up in the overheated state will grow to infinity, right? But with a gamma that's between 0 and 1, or a true time limit, then it's finite. Does that make sense? Okay. So how do we know that this is going to converge? Again, we assume that there's some minimum reward, we assume there's some maximum reward, and we assume that gamma comes from, let's make this non-inclusive, right? Okay, so let's say that the tree actually does have a maximum depth n. Then you just do this n times, right? You reach the bottom of the tree, it's expected maximum depth, right? That's the true value. Okay, so the more interesting case, there is no bottom to the tree, right? And so this is kind of going to be a little hand-wavy, but this is the general concept for how we'll improve this. It's a contraction argument at the end of the day. There's a more formal way to do this, but it's a lot more complicated. So let's just kind of conceptualize how it would work. Okay, so any state bk and bk plus 1 can be viewed as a k plus 1 expected max search from there, right? And the difference in the case of bk plus 1 is we have this extra layer down here, right? And this extra layer has some values, but we've bounded those, right? So in the worst case, they're all R max or maybe R min, right? We can conceptualize these two things as the same if we fill all of these with zeros, right? So then we also note that everything in this layer here is discounted gamma to the k, right? So what we can do is we can relate the worst case value here, which is going to be multiplied by gamma to the k, to the value here, and at most, they're going to be different. This is like an element wise max over these. But since this is bounded, there is a k large enough that we get arbitrarily close to the true solution, right? And so as k increases, this bound contracts, right? And that's convergence. And it's waived, right? There's some details missing here, but that's kind of the general concept. Okay, so let's move on. Actually, let's take 5 minutes. My 5-minute alarm went off a long time ago, so I'll give you your 5-minute break now. When we come back, we'll start talking about ways to actually get policies or to evaluate policy details.
Yeah, well, I mean, it was getting closer for, like, yeah, it was like maintaining it. Here's what it's do. Yeah, someone Oh, I rewarded it for not going backward and not Yeah, I did look at your stole but not Oh, really? Oh, so you did look at it. Sweet. That helps. Push it a little forward. Like keeps going. Pretty well. Yeah, yours is good. That's funny. It's like sticking over. Yes, this is reflexation. Yeah. Block top on the other side of the net. Oh, they like, yeah, they like block it. They made it. That's funny. What? Yeah, so what I was doing, yeah, I think I made these like relative to there's like different like things here. When it's like running away, it's like it doesn't run away, it goes away and stuff. Oh yeah, I think my variable is ghost prime or something. Yeah, so I created ghost prime. Right, and it flips depending on if it's have five stars food in two different ways. Some of the default people in default board. It's like a bunch of things together. What I want to try is adding a one that doesn't have a capital letters like the ghosts in your body. Ghosts in your body. Yeah, I guess it's kind of Oh yeah, there's a way to get the ghost. Oh, you can access a ghost object and get those. Yeah. I just found that like that probably works too though. Yeah, it works because presumably this is the same stuff. There's like two different ones, like
Okay. Alright. I'm grumpy at myself for not having done this right the first time, so we're gonna do it again. You guys groaning? Is that? Alright, well, we're still doing it again. Okay, so we're finding this value. Spoiler alert, right? Okay, so from here I have two actions, right? I'm going to take the max of the two, so let's look at each action. So let's say that I go slow, right? Then we need to sum over the possible resulting actions. If I go slow from here, there's only one place I can end up, right? And that's cool, right? So this probability is 1.0. The resulting reward is I get 1 for going slow right now, plus the optimal value of having been slow, right? Stu? Does that make sense, everybody? Okay, if instead I go fast, that's where it's more complicated, right? Because there's S prime is equal to cool, right? For this first case, there's a 0.5% chance that happens. The reward I would get right now is 2, right? Plus the optimal value from cool, right? This is defined over where we're landing, which is 2, right? By this. Plus, there's the possibility that I end up in warm, right? I get 2 right now, but the optimal play for warm is 1. This is 3.5, right? So the sum is over the possible destinations. So we ended up either in cool or warm, right?
And so the calculation for ending up in cool was or the value.
So if I go fast from cool, that's what this is. That with 0.5% chance I will end up in cool again. Because I went fast, I get this 2, and because I'll play optimally from cool, that's a 2.
So the S and the F there are the actions, right? Not the states.
Slow, fast, yeah. So I'm maxing over these, that's what this is. Right?
Maxing the actions, okay. And then each action is the sum of the, okay, yeah.
Cool. We good?
Yeah.
Alright. Arithmetic, I haven't planned on under fire, it's not my strong suit. But, we feel good? Okay, so let's continue. Policy methods. So let's say somebody hands you a policy and says, is this good or is this not good? We want to be able to answer that question. So we need to be able to evaluate a given policy, right? And so we look at this expect max tree example of how this is working, and things have changed in just a very specific way, right? In the past, we were doing an optimal action, which meant reasoning over all of these possible actions from our current state, right? But if we fix the policy, it's just one arrow. That's what the policy is, right? The policy is that arrow for every state, right? Given a state, you have an action. You have one for every state, that's a policy. Or if you can compute one for every state, that's an implicit policy. But that's what that means, right? So now we don't have to reason over those other actions. But we may not be optimal anymore, right? Okay, so let's talk about what the utilities values mean, because they're going to be slightly different if we have a fixed policy, right? So we want to be able to compute the utility of some state S, similar to how we were doing previously. What's the utility of this state? Under a fixed policy phi. So in the past we had V star, right? We're going to get rid of V star. We're going to have a different V. It's going to be V pi of S, right? Just a different kind of notation. And this is the expected total discounted reward starting in S and following pi, which again, may be a bad idea, but is what's given to us, right? Okay, so similar to how we did last time, we can define the Bellman equations for this, which gives us kind of what this is defined as if we look forward one step, right? And so, again, doing this without looking forward in the slides, what would this be? So A is given to us, so we don't have to max over the A's anymore, right? So when you take the sum over where we may end up of S, this A is now pi of S, right? That's what it means to be a policy. S prime. This is still probabilistic, right? The policy just tells us what action we should try to take. It's not going to describe what happens after we take that. That's still non-deterministic, right? We need this times the rewards, right? So there's some reward that's defined over where we started, the action that we took, again, given to us by the policy, and where we ended up, right? Plus gamma times what will happen if we follow the policy in the future from S prime, right? So I've changed all of the stars to these pi's. It's not optimal necessarily anymore. And now I don't have to reason over all the possible actions because I'm given the actions, right? Does this make sense? This is almost the same equation, but not quite. But if you spend a long time with these equations, like I suggested, then you can kind of reason through, like we just did, what the specific version should actually be, given the specific instance of the problem you're trying to solve. Right? Okay, cool. Is that the same? We did it. Awesome. Okay. Here's two policies. So here we have this robot trying to get through Gridworld. We've got these fire pits on either side, and the robot's got two plans, right? Not plans, that's a terrible way to describe that. Two policies, right? Defined over all the states. One of which says always go right, and one of which says always go forward. One of these is better than the other, right? If not fire is your goal. Both have a chance of ending up on the other side of this bridge, right? But one of them is going to provide you with a strategy that's going to be successful a larger percentage of the time, right? And your expected utility is going to be greater. Okay, so if we look at what the policies, what the values might actually be in this specific instance of Gridworld, this is kind of what you get, right? So we're exiting out of the sides, we've changed it from -1 to 10 and the +1 to 100 instead. That's all just a description of the problem, hasn't been to do with the actual, how we solve it, right? But you can see even this square here has a positive value, right? Because even if you're trying to go right with some non-zero chance, you're actually going to end up here, and then hooray, we accidentally won. But it's not looking so good from down here, right? Okay, so let's say we have an algorithm for evaluating policies, right, which we kind of just described with a different set of Bellman equations. You can do a similar update, right? The complexity of that would be simpler, right, because there's no A term. Well, now we have an algorithm for finding the optimal policy. Right? What is it? Write down all the possible policies, evaluate how good they are, and then rank them, right? And just pick the best one. What's wrong with that? Yeah, it probably is pretty expensive. Not true. It's possible here, right? Which would just be what? How many possible policies are there here? 4 to the 4. Right? But won't be possible in non-trivial problems. But this brings up the point that we can start to search over a set of possible policies, right? Or optimize using optimization tools over the policies, right? And in this way, we can start to find better and better policies potentially, and converge towards something that's optimal, which is what we're going to do here in a second. Okay, but how do we actually evaluate how good a policy is? Well, as I mentioned before, we could do a similar trick to what we did last time, which is to turn those Bellman equations that are describing the pi into a set of updates, and do exactly what we did with value iteration. Right? So we know that v pi of 0 is 0. We can describe this relationship. This is slightly different, right, because we're no longer maxing over the a's. But other than that, and the fact that these are being described by your policy, it's the same. Right? So you just do this. It's computationally less complex, right? Because you're not worrying about the a's. It's linear, which is great, because now you can solve it with any kind of linear solving method, of which there are many very fast ones. Right? It's a lot easier to solve. Okay. Computationally speaking, we're looking at order s squared versus the cardinality of your state space. But again, that's the worst case. Only if you can transition from every state to every other possible state. In practice, really less than that. Okay, and as I mentioned, without the maxes, this is now a linear system of equations. And so you can use pre-built linear system solvers to do this. What if you're given values and you want to extract the optimal policy for those, or the policy described by those values? Yes?
So once you have the values, do you just sum them all up and say whichever one's higher?
Well, you need some way to rank the quality of policies, right?
Yeah.
And maybe that's one way. Maybe you have a start state and you just look at the expected value from that start state, and that's how you would rank your policies, for instance.
Or a specific problem.
Or a specific problem, but if you're looking at policies over a more general set of problems where you don't have a start space, for instance, that might be one way to do it. Some statistics over those values, it could be the sum or the max or the sum of the squares or whatever. Okay. So what if we're given a set of values, and again, ignore the arrows, and we want to compute the optimal set of actions? So let's say we're here, and all we have are the numbers. How do we decide what to do? Yes?
Greed works great here.
Does it?
In this example, from 0.89, we go right up to 0.98, and
So that's a policy, but it's not the optimal policy in this case. Right, we've seen this kind of weird behavior that we highlighted a bunch both last class and this class, where from this square, the optimal policy under some set of assumptions about decay and things and linear rewards is to go left, right, and hope that you kind of chance your way into the square above it, rather than going straight up and having the risk of falling into the pit of doom over there, right? So you can't just look at the values. It's actually a little more complicated than that. Maybe it's much more complicated than that. What do we do? It's not obvious, right? Just looking at it. We need to do one step of expect max for that. That's the answer. So, again, we're looking over all the A's, right? We're trying to pick from the A's. And we look at what's the expected utility of those A's, right? This is the Q values. We take the max Q value and we return the A that corresponded with that, right? Does that make sense? So the key insight here is this isn't max, it's argmax, right? Have you guys seen this before, this notation? So max returns like a real value, right? What is the value? So you don't want the value, you want an action, right? So argmax is just the notation in math we use for this kind of thing that says this function argmax is returning the value that maximizes the equation, right? Does that make sense? Okay. If you haven't seen that before, think about it for a minute, but okay. This is called policy extraction, since we're extracting a policy implied by the values. Right? What if somebody gives us all the Q values? How do you extract a policy from this? Now, greedy is the right answer. Right? Before we were just picking the argument that gave us the maximum value here, right? We have the maximum value there, just pick the best one, go on with your day. Right? So actions are much easier to select if we have a set of Q values rather than if we had a set of values themselves. This is an insight that started to bring the community forward in reinforcement learning, which we'll talk about next time. We're behind a little bit again, and this is very important, and it's going to take longer than 2 minutes. So at this point, are there any questions about what we've covered today? Yes?
How is this tree in terms of like versus the old way of doing it?
So here, you find yourself in a state. You have each of the Q values, you just pick the best one.
Gotcha.
Something happens, be a chance you resolve, you pick the best one from there. That's the optimal policy.
Okay.
Whereas in the other one, you have to reason about it.
Yeah.
So, looking at these Q values, the policies that we made were based on
Yes. But you have to do
the reason I was thinking about here was because I thought there was 80% chance of
Oh yeah.
so I was like going left is risky.
So this is kind of specific behavior associated with this